Okay, so the plan for today's session is to finish up chapter 12 and then do some practice runs for the first midterm coming up next Thursday. Um, so let's first start with the halogenation or addition of X2, where X is usually chlorine or bromine to alkenes. And there are two different scenarios. It could be in a non-nucleophilic solvent. So you could see things like CCl4, CH2, Cl2, or CH3NO2. If you see any of these solvents here, they will not do anything in the reaction. You just ignore them. Or you could just see X2 by itself. And if you just see X2 by itself, then no other solvent is going to compete and react. So the way I'm going to do these are that I'm going to show you the general reaction of what happens and then show you the properties of these reactions and then the mechanism afterwards. So let's say we have an alkene like that, and we put that through Br2 or Cl2 under one of these non-nucleophilic solvents, CCl4, CH2, Cl2, or CH3NO2. What we are going to get is an anti-addition. So let's say we use the Br2. Both carbons of the alkene are going to have a bromine on it, where both of those bromines are anti to each other, opposite from each other, right? It could be that, or let's say there was like some kind of stereochemistry. You could flip it as well, but it could have been this as well. But they're identical in this case because you could just flip it upside down and then you get the same thing, right? So when you see X2 with an alkene with a non-nucleophilic solvent like this, you just add the X on both carbons of the alkene, and they are going to be anti to each other, right? Where for this reaction, the product is going to be a trans vicinal dihalide. So this is a trans vicinal dihalide where vicinal means that they are adjacent to each other. Dihalide because we have two halogens and then they are trans to each other. Trans, vicinal, adjacent, two halogens. Trans vicinal dihalide. The stereoselectivity of this reaction is going to be anti-addition because we see that the two halogens are anti to each other, right? The regioselectivity of this reaction is none. There's not Markovnikov or anti-Markovnikov because we see that the two groups are added onto the alkene are the same group, bromine. But we will see regioselectivity for the next scenario. Okay. And the intermediate of this mechanism is a cyclic or bridged bromonium or chloronium ion. Cyclic, bridged bromonium or chloronium. Ion. Okay. The mechanism is called electrophilic addition. And in this case, since we do not have a carbocation intermediate, we are going to have no rearrangements, no carbocation shifts like hydride shift or methyl shift. No rearrangements. We only get rearrangements whenever we have a carbocation intermediate. In this mechanism, there are no carbocation intermediates formed. Right. So let's go over the mechanism now. Let's say we use Br2. I'm going to draw out the Br2 like that, right? The alkene, you can think of that as a nucleophile because there are a lot of electrons in that double bond right there. One of the carbons is going to attack the bromine, one of the bromines of the Br2, and then we're going to kick out the other bromine as the leaving group. As this bromine here is gaining electrons, that bromine is becoming more negative. Since this alkene is losing electrons, this alkene is becoming more positive. So this is becoming the nucleophile. This is becoming an electrophile. So this bromine here is going to attack the other side of the alkene at the same time, forming that cyclic bromonium ion. Yeah, this right here initially is delta plus, right? But as this alkene is donating electrons to the bromine, that delta plus is going to become delta minus, which that delta minus is going to come back around and attack the other side of the alkene. Because once this alkene is losing electrons, it's becoming delta positive, right? And this happens simultaneously, forming the cyclic bromonium ion intermediate. Okay, so let's say we know that these two carbons here are flat and planar. So that means that the bromine could attack on the top side, becoming a wedge, or bottom side, becoming a dash, right? So I'm going to show you both scenarios. And the formal charge of the bromine in this cyclic bromonium ion is a positive charge because this bromine has two bonds, and halogens with two bonds will have a positive charge, right? So let's say this was a front side attack on the top, and then the bottom was a bottom side attack. We see that the Br that got kicked out is going to be Br minus, right? And in this case, it doesn't matter which carbon the Br minus attacks. Let's just say that this Br minus attacks that carbon right there and kicks off that bromine right there. This is going to be an SN2-like reaction where that dash bond that got broken off will invert into a wedge bond. Right, so that becomes wedge bromine here, dash bromine there, right? And this is why this is anti-addition, because we see that the two bromines are opposite from each other. We could do the same for the top side, like this, where that wedge bond would invert into a dash bond like that. And that is also anti-addition because that is anti to each other. Yeah. So it will be more accurate to show the one as wedge, one as dash, to show that they are anti to each other. Because if you drew them as flat bonds, there's a possibility that both are wedges and both are dashes, and that won't show that it's anti to each other. Right? Yeah. Yeah.
Bromine, the negative bromine that can liquefy will always attack the more substituted side.
Yeah. It's more accurate to say that it attacks the moist substituted side because think of it like an epoxide in acidic conditions. The moist substituted side will give you the more stable carbocation intermediate, which is why it will attack the moist substituted side, right? It's the same as if we had water or alcohol, which is the next reaction we're going to do. It will always attack the moist substituted side of the bromonium ion, right? Okay. Any other questions on this reaction? Okay, let's move on to the next scenario. Or you guys need some more time on these notes? Okay, let's move on to the next scenario, where instead of having a non-nucleophilic solvent, we have a nucleophilic solvent like water or alcohol, H2O or ROH. Right? So the general reaction, let's say we have the same alkene, and we have Br2. And in this case, I'm going to write water in blue and then alcohol in green to show the difference. And let's make this substituted as well. Okay. Let's have that there. What we are going to get here. Where if our solvent was water, the thing that attaches to the alkene is an OH. If our solvent was an alcohol, the thing that attaches to the alkene is an OR group. And the R group depends on what they give us in the question or the problem. And we noticed that the water and alcohol will attach on the more substituted side of the alkene. And do you guys know the name of that principle where the nucleophile attacks on the more sub side of the alkene? Yeah. Yeah, Markov-Nakov, that's right. And we also see that these things are added anti to each other. So the stereoselectivity is anti-addition as well, right? So for this reaction, the product is going to be a bromo alcohol or bromo ether, depending on your solvent. It will be bromo alcohol if you used water. It will be a bromo ether if you used an alcohol as a solvent. The stereoselectivity of this is anti-addition because we see that they added on the opposite side of each other. Stereoselectivity, anti-addition. And the regioselectivity, like we said, this is Markov-Nakov. The intermediate of this mechanism is going to be the same thing, cyclic or bridged bromonium ion. And the mechanism is also the same, electrophilic addition. Okay. And in this case, we also see no rearrangement step because we did not form a carbocation intermediate. So we don't have to worry about a hydride shift or a methyl shift. So now let's go over the mechanism of this reaction. Let's say we have Br2. This alkene here is going to attack that bromine, like we did in the previous example, kick out the other bromine as a leaving group. And then this bromine here, as it's gaining more electrons, is going to be the nucleophile that's going to attack this alkene that is losing electrons and becoming the electrophile. So it's going to come back on the other side and form that cyclic bromonium ion intermediate. And in this case, it could also attack on the front side or the back side. If it attacks on the front side, becoming wedge, that becomes wedge bromonium ion. And that forces this flat methyl group to become a dash. Yeah, this is how I see it. But during Pascal's lecture, he drew the bromine leaving first, giving that bromine a positive charge. But this is like the more accurate way to draw it. Yeah, it means the same thing though. Yeah. Right. Because yeah, the bromine like it needs to have a reason to leave. Which the reason to leave is this reaction happening here. Yeah. Yeah, this here is the bromonium ion, cyclic or bridge bromonium ion, where that bromine will have a positive charge because it has 2 bonds and 2 lone pairs of electrons. And that's the front side attack because we see the bromine is wedged. In the backside attack, we see that the bromine is going to be dashed. And that forces the methyl group that we had in the alkene to become a wedge, like that. Okay. So now let's say we had water in the mechanism. Wait, first, we know that the Br minus got kicked out, right? And we have water in the solution. This seems like a stronger nucleophile because it has a full negative charge. And we learned that full negative charges are stronger nucleophiles than neutral molecules. But the reason why water is going to be a stronger nucleophile than bromine is because we have 1,000,000 times more water in the solution than bromine does. So this is an excess which overpowers the bromine nucleophile, and this will serve as the nucleophile instead, right? Because there's only a little bit of bromine minus compared to 1,000,000 times more water. So that's why in nucleophilic solvents, we get a different product. So that water there, the nucleophilic atom is the oxygen with the lone pair. That's going to attack the carbon that would give you the more stable carbocation, which is the more substituted carbon. So this water here will always attack the more substituted carbon, right? Which is going to be like that. And we're going to break open the bromonium ion like that. And this goes through an SN2-like reaction as well. Well, not exactly SN2, but similar to a backside attack where it inverts the stereochemistry. So, let's see. We would get that and this, where we invert the stereochemistry of the bond that we just broke. Right? And what is the last step here? How can we neutralize that positively charged oxygen? Yeah, we could deprotonate it, and you could use either Br minus or water, doesn't matter. Well, it's more accurate to use water because there's a lot more of it. Right? So we just use that to deprotonate it and neutralize it to give us our final products. So when you draw the answer, you could draw it like this, OH, Br, and then you can say that they are enantiomers of each other. Well, when can you not do this? When can you not do this symbol? Oh, this right here is going to be like racemic. Like one is dextrosatory, one is liberatory. Yeah, that's right. Because let's say we had existing stereochemistry like that. The other product would be just these two carat centers are flipped. This one does not change at all. Yep, those are diastereomers. So if you had a pre-existing chiral center, don't do that. Yeah, you can only do that when all the chiral centers swap. This means enantiomers, right? Or you could say plus enant. Right. Oh no, because if you drew it as planar, then it shows that there's a possibility that they are syn to each other. Because you know how this reaction is anti-addition. If you draw it planar, then OH and Br could be both wedges or both dashes. Yeah. Yeah, so if we used Br to deprotonate this positively charged oxygen, then we would form HBr. If we used water to deprotonate that oxygen, we would form H3O plus. So we would always have an acidic side product, HBr or H3O plus, depending on what you use to deprotonate. Yeah, but in HBr would be more minor than this one because water is like 1,000,000 times more in excess than the Br minus. So this is in reality more in excess than HBr. But if you do this on exam, you won't get points off. You can use Br minus to deprotonate. Uh-huh. Yeah, it's gonna be so minor, we don't include that as the major product. Yeah, but it could happen. It could happen in the lab. Yeah, because Br minus is still out there floating around that could attack one of those, but there's so much more water that we just ignore it basically. Okay. So let's say here, wait, actually practice. Oh, okay. When we're back in 118A, what is one way that we could form an epoxide? Like, what is one reaction name? Yeah, MC3A is one from an alkene, and also Williamson ether synthesis, right? Williamson ether synthesis. Specifically intramolecular one. And that's a big sign if you see an alcohol adjacent to a good leaving group like bromine. It's most likely bromine, adjacent to bromine. Right? So let's say that we had this alkene here, and we put that through Br2 and water. We know that this will be an anti-addition where one carbon of the alkene has the OH, the other carbon of the alkene has the Br, and they are opposite sides of each other, right? And let's say we introduce a strong base like NaH or NaOH. What do you guys think is going to happen here if we introduce a strong base? Yeah, it would make an epoxide where the first step is that the strong base is going to deprotonate this alcohol hydrogen, become O minus, and then that O minus comes in to do an intramolecular SN2 reaction, kick out the Br to form the epoxide. Right? I saw this on the midterm for last quarter, so this might show up on the midterm. Like you use Br2 in water, which is the new reaction you learned. Predicted product problem, where it showed up like this right here. 1 Br2 water, and then 2 NaH DMSO. So I'm going to show you like how we get to the epoxide just in case. The H minus or OH minus grabs that hydrogen right there. The bond between oxygen and hydrogen goes off and goes to that oxygen right there, forming your alkoxide ion. That alkoxide ion is going to do an intramolecular SN2 reaction now by attacking that positively charged carbon and kicking out the good leaving group bromine. Right. This also like inverts the stereochemistry, so we're just going to say that. Oh, epoxide right there. And in this case, since there are no other pre-existing chiral sensors, we could do plus the enantiomer or that symbol to show that it's a racemic mixture. But if there was another chiral sensor somewhere in the molecule at the beginning, do not put that symbol because they would be diastereomers instead. And then this reaction will be a diastereoselective reaction. Yeah. Yeah. Show dashes and wedges for the thing here for both products because that's the only thing that's changing. And then the other chiral sensors would not change. You keep that as the same.
That the bromine and oxygen alcohol swap. That's also possible, right?
Yes.
Would that
Yeah. If this is symmetrical, yes. But let's say this was like an extra carbon longer, then those would be different products. Yeah. In this case, they could be wedges, which I've shown it as that symbol right there. Yeah. And let's see, what's another thing I was gonna say? Also, like if this carbon here, like one of the carbons is more substituted, the OH is going to be on the more substituted carbon of the alkene because of the more stable carbocation intermediate for the mechanism. But in this case, both alkenes are equally substituted, so It didn't matter where the OH ended up in. Yeah. No, you don't have to show how you got the hydride. It just comes from what they give you right there. Because whenever you see Na, it's always positive charge. So you assume whatever is attached to it, always negative charge. Instead of a hydride, you could also use OH minus. Or yeah, OH minus or NH2 minus. Any strong base. Strong base. Okay. Now let's try these practice problems here. Oh, actually, let's just do two of them just to save time and move on to the next reactions. Let's do 3 and 4. 3 and 4. And then you guys could try the other ones as extra practice after this. Some of them are from the AETC. Some of them I made. Yeah. The first two are or like some of the, yeah, I forgot which ones are from AETC. Oh, 6:30. Dang.
Yeah.
Ocam discussion or no? Oh, physics discussion. I see. Yeah. Oh yeah, yeah. Thank you. Yeah. Oh, didn't you have a physics quiz like this week? I heard you guys the physics week had a quiz. Oh, Wednesday day. Yeah. Okay. Have you guys signed it? Yep. Oh, thank you. You guys signed this? Yep. Did you sign this? Oh, yeah. Oh, did you sign in already? Oh, I see. I see. Hi, can you guys sign in, please? Thank you. Okay, thank you. Thank you. Thank you. Hi, can you guys sign in, please? Thank you. Yeah.
This the that moving with the campaign.
Yeah, so this reaction here can never do rearrangement. So when you see X2 in some kind of solvent like H2O or ROH or CCl4, any other solvent, that would never do rearrangement because you know how in the intermediate it forms that kind of ring with the bromine and it never forms a carbocation, right? So there's no rearrangement possible. If we do have HX instead, for example, like HBr or HCl, then there's rearrangement possible because that mechanism goes through a carbocation intermediate. And whenever you have a carbocation intermediate, you always have to stop and look out for hydride or methyl shift.
Oh yeah.
Yeah. Yeah. You don't have to look out for that here. Yeah. Are you signed in yet? Oh, you can hit. Sorry. Thank you. Can you sign it, please?
Yeah.
So we're gonna finish up chapter 12 hopefully, and then do practice runs for the midterm.
Okay.
Yeah. Like finish up all the reactions.
Okay.
Yeah. Huh? Okay. Yeah. Bye. See ya. Okay. So what's the very first step of this mechanism here? Yeah, formation of the bromonium ion ring, where in this example here, there's actually a side that the ring prefers to be in. Do you guys know which side it prefers to be in? The back side. Right, because the methyl here is on the top side, which introduces steric hindrance. Right. Yeah, two major products and two minor products. And then from here, we are going to use water to attack the moist subside. But we see that these carbons here are equally substituted. So the water could either attack this carbon or that carbon right there, giving you two different products. So let's do that. I'm going to show the mechanism of only one of them. So then I can just draw the products for the other one. And then we could use water or bromine to deprotonate the positively charged oxygen and give us our neutral answer here, neutral product. Br OH. If the water attacked on the other side, we would get this product here. So let's say we had this intermediate instead, where the ring was on the top side. Right? Then we would get these two products here. Right? Dash OH R, that one, and so these are four different products. It came from the two different possible intermediates where the ring could either be on the top or bottom side. And then from there, we could make two other products based on where the water attacks on which carbon. Where I would say that these two are major over these two because it comes from the more stable bromonium ion intermediate. Yeah. Let's see. So this came from the AATC website practice problem, which is like based on the series lecture class. For Mascal's class, I would include all of them and label major, major, minor, minor, just in case. Yeah. So it will matter if there are other chiral centers around and how bulky it is. Like in this molecule here, the top side has a wedge methyl group where this is probably gonna be more stable than this one, but this will still happen. Like it doesn't matter if like that wasn't there at all. Like there's a 50-50 chance of each. But in this specific molecule, let's say this is like 60-40 chance. Like this is more major because the bromine prefers to attack on the bottom side, since at the top side there's more steric hindrance. But just for the exam, they wanted both all of these answers. I mean the ATC worksheet. Yeah. The answer didn't say anything so about it, but I would say that these two are major over these two because these two came from this intermediate, which is more stable than this intermediate right here. Right. Yeah. But the answer included all of these as the major products. Okay, let's move on to the next one. This one here is a tricky one. So the first step of this mechanism is that the alkene is going to attack the chlorine, kick out the other chlorine, and then the chlorine that got attacked attacks the other side of the alkene at the same time, right? And that would form our chloronium ion, where in this case, it doesn't matter where it attacks on the top or bottom side because there are no other stereochemistry, and that's why there's a 50-50 chance. I'm going to choose that chlorine ion to become a wedge, chloronium ion, right? So we see here in the reagent, there are no solvents given, like no CCl4, no water, no alcohol, right? But what do you guys notice about this here? What other functional group do we have in the molecule, in the intermediate? Alcohol, right? So this alcohol here is going to attack the chloronium ion. This is an intramolecular reaction where the nucleophile is on the same molecule as the electrophile. If that's the case, this is an intramolecular reaction, which will always form a ring. Which carbon of the chloronium ion would the alcohol attack? Yeah, the more substituted side, which is this one here, because it will make the more stable, like carbocation-like intermediate, right? So it's gonna attack there, break open the ring, and we're gonna invert that stereochemistry. Oh wait, this is intramolecular. So to keep track of everything, start your number 1 atom at the attacking atom, and then number it all the way to the atom being attacked. So our oxygen is 1, 2, 3, 4, 5, 6. We stop there because that's the atom being attacked. We know that we are going to form a 6-membered ring where one of the atoms of the 6-membered ring is an oxygen. So let's draw that template out. That is a template of our answer where there's a 6-membered ring and the first atom is oxygen. We see at carbon 6, there are 1 and 6. 1 and 6. There are 2 methyl groups, which those 2 methyl groups are right here, 1 and 2. Right? If on carbon 3 there was an isopropyl group in the reactant, then you just include that isopropyl group there on carbon 3. Right? And on carbon 5, we see that there is a chlorine that is wedged. Yeah, that's what I was thinking about because 1-1 wedge. Oh, so since this is not a chiral center, we don't have to include stereochemistry. Yeah. If this was a chiral center, then we would include stereochemistry. Oh yeah, and the complete mechanism wouldn't be that because we see that the atom oxygen still has a hydrogen, right? Where the very last step is just to deprotonate that positively charged oxygen to neutralize it, if this was a mechanism problem. But for predicted product, you could just skip straight to this answer. Yeah, because it's not given. That's why we can't use water. And if water was given, right, then there would be actual competition between that alcohol and the water, because the water and alcohol can attack water. The alcohol here is probably going to be the faster one because intramolecular reactions are faster than intermolecular, but we still get mixed products of the water attacking instead of that alcohol. You could use Cl minus, the one that got like kicked out, or you could use another version of this alcohol here to deprotonate it. Okay. Yeah. Oh, so that was a choice. Yeah, no problem. You could make the chlorine wedge or dash. It could have been dash as well, like dash chlorine, and then wedge methyl. Yeah. And in this case, we do have enantiomers, so we can do that symbol as well. Yeah, or plus enantiomer. That's the same thing, right? But you cannot do that when there is a pre-existing chiral center somewhere else, because those will be not enantiomers. Yeah, yeah. If it already has a, yeah, because those will be diastereomers instead. Yeah, yeah. Yeah, so this is not a chiral center because those are two of the same groups, right? And if that's not a chiral center, then we don't have to include wedges or dashes there. Oh, then that would, yeah, we would have to, that this would be diastereomers, and we can't include that symbol, right? If that wasn't ethyl. Yeah, you have to draw out the ethyl and wedge or dash there. Yeah, yeah, miso. Then yeah, that's not going to have any optical activity, not chiral at all. So no plus minus, not diastereomers, not enantiomers. Miso is achiral. If there was a plane of symmetry. Yeah, chirality. When you start with an achiral thing and then you create a chiral thing, it's most likely to be enantiomers only. But when you start with a chiral thing that already had an existing chiral center, and then you react with that and create more chiral centers, those are most likely going to be diastereomers, right? And it will actually depend on the shape of the molecule as well, because if there's a plane of symmetry, then you could have a possibility of meso, where there's no chirality at all. But most likely, it's either going to be enantiomers or diastereomers only, right? Yeah. But that's good. Like you talk about like the chiral, like the plane of symmetry for meso. Okay. Now let's go on to oxymercuration, demercuration, where the general reaction of this. Oh wait, first let's say we do this and we put this through H2SO4, water, and heat. What product do you guys predict here based on these? Yeah, on this side right here. So this is the tricky thing here. You know how the mechanism is that we form a carbocation here. Whenever you form a carbocation, you always stop and look out for shifts. In this case, we could do a hydride shift, where the carbocation will be here, and then the water will attack that carbon instead, right? So our answer here, given those reagents, would be that right there, right? But let's say for synthesis, we wanted this, like the one that you said, right? If we wanted the alcohol here, yeah, yeah, yeah. H plus will always bond to the less substituted side of the alkene, and the carbocation will always go to the more substituted side of the alkene. If you wanted this answer here with no rearrangement at all, then the reaction here is oxymercuration demercuration. That reaction does not have any rearrangement, so you could select for this Markovnik composition without worrying about any shifts. Okay. And the reagents for that, yeah. So you could have water or alcohol. Or NaOH and water. If you used water, then your product would be OH, alcohol. If you used ROH, alcohol, your product would be OR, an ether. Right. So you have to be careful and look at what they give you in the reagent, water or alcohol, because that will tell you what kind of product you'll get, alcohol or an ether. Yeah, this reaction would be also anti-Markovnikov, right? So the product for oxymercuration is either going to be an alcohol or ether. The stereoselectivity is going to be anti-addition, and we will see that in the mechanism, where the OH or OR is anti to the mercury. The regioselectivity, we said it was Markovnikov because the OH or OR attaches to the moist subside of the alkene. Yeah, no rearrangements, that's right. Because we do not form a carbocation intermediate. Whenever you form a carbocation intermediate, there's always a chance of rearrangement. The intermediate in this case is a mercurium ion. Intermediate mercurium ion. Mechanism is still electrophilic addition. Most of these reactions are electrophilic additions. And no carbocation rearrangement. Because no carbocation intermediate. So what OAC is this right here, where this is the O and then the AC is basically that acetate group here, the carbonyl with one methyl group. That's OAC. When we have HgOAC2, this is what it looks like here. This is HgOAC2 because this mercury is bonded to two OACs here. Let me put this in a different page. Where this OAC here is a really good leaving group because when it leaves, it will leave with a negative charge. And this negative charge on that oxygen is really stable because of resonance. This negative charge here can do resonance with a carbonyl. And if it's really stable, it's a really good leaving group. The mechanism is going to be very similar to the X2, where one of the alkenes, carbon, is going to attack the mercury, kick out one of the leaving groups, the OAC, and then the mercury is going to come back and attack the other side of the alkene, forming your mercurium ion. Right? In this case, it doesn't matter if it's wedge or dash. Let's just say that it is wedge, but it could also be dash as well in this case. Right? And if we have one OAC left, where this mercury with 3 bonds, we have a positive charge there. Right? Now, your leaving group that left is this leaving group right here, the acetate. And let's say we had water floating around, H2O. Which one is going to be the nucleophile here? The acetate with the full negative charge or the water? Yeah, so the acetate here looks like it's a stronger nucleophile, but you know, remember back in the X2 with water, water is a million times more in excess in it. Water is going to overpower the acetate. And another reason is also that this negative charge can do resonance, which makes this a weaker nucleophile. Right. So this water here is going to attack the more subside of the mercurium ion, just like the X2 reaction mechanism. Do that. And then we're going to break that open right there. Right. So we're going to invert that wedge into a dash. And then that will become this. Where this bond right here is supposed to be a wedge, but I got rid of that wedge because that's no longer a chiral center. if that was a condensate site, then we would keep that as a wedge, right? Well, let's just write it just in case, just to make it clearer. Where this is a wedge because it stays unreacted at that carbon right there, right? And we see that this is anti-addition because the water or alcohol attaches on the opposite side. Yeah. Yeah. You could write HGOAC instead. Yeah. Your TA will be able to understand that. Instead of this, you could also write HGOAC, which is probably faster. This is OAC. Yeah. That's why I originally put it as planar. But the reason why I put this wedge is to, yeah, technically a wedge, right? And also to show why this is anti-addition, why the reaction is anti-addition. Yeah, just to show that they're anti, right? Where this is actually planar because you know how this is a single bond, it could rotate, it could like, yeah. Yeah. Yeah, the water or alcohol will always attack the moist subside of these triangle rings. Because you know how we get like a bromonium ion ring, a chloronium ion ring. If you had a mercurium ion ring, then it's the same exact principle. We always attack the moist subside of the ring, okay? Because that will give us the more stable carbocation intermediate. But like it is a form of carbocation, but there's more positive charge character there. Oh, this one here? Yeah, this one here, there are two other carbons attached to it. This one here, there's only one carbon attached to it. Yeah. Yeah, the water becomes a dash because think of it as an SN2 like backside attack where it will invert stereochemistry. It attacked a wedged bond and broke it up open, which became a dashed bond right there. If this was a dashed ring, then that water would become a wedge. And this will stay as a dash to show that they are still anti to each other, anti-addition. Now that's the end of the first step. The first step where we had Hg, OAC, what was the other one? H2O or ROH and THF. Now let's move on to the second step. Oh, wait, actually, there's one more thing that we could do. We could neutralize this positive charge oxygen by water. Right. Neutralize acid-base reaction. Give us this neutral OH, HG, O. Now, this is the second step here, where we bring in our reducing agent, NaBH4. When you see NaBH4, always think of a hydride ion, an H- ion.